Hello students, welcome to video lesson 811. We're going to do this section and two more in chapter 8, but just one more video before we wrap up our year. I wanted to do this video because this is one of my favorite sections in Pre-Calc. I think it's one of the most interesting, one of the most useful for calculus, particularly when we get to calculus and start talking about limits. This is going to help us to have some foreknowledge of some things about limits when and if we get there. So back in chapter 5, we began talking about limits. We introduced what a limit is, right? The value that a function approaches as the x value approaches something. So we did limits as x approaches 4. We did limits as x approaches 10. We did limits from one side as we came just from, the negative or just from the positive. We also did limits as x approaches infinity. And that's what we're going to focus on today, limits as x approaches infinity. And then we will also look a little bit in your practice problems at approaching negative infinity. Okay, so if we look at a few functions and just talk about, remind ourselves what it means to find a limit as x approaches infinity. Here we have, let's say they're asking us to find the limit of f of x as x approaches infinity. F of x is 4x squared. Okay, so 4x squared, if we were to just real quick think about what the graph of this would look like, it can be helpful for thinking about this limit. The graph of 4x squared is going to look something like this, right? And so as x goes towards infinity out this way, the y is going up very quickly, and it's going to go up forever, and it's going to continue to do that no matter what. So the limit as f of x, the limit of f of x as x approaches infinity is infinity. Okay. The next one asks us for the limit of g of x as x approaches infinity, and then g of x we are told is the square root of x. So if we think about what the graph of this one looks like, it starts here and does this kind of thing, right? And it sort of goes up and flattens out. But does continue to get higher and higher. So as x is approaching infinity and going out that way, our y is going up. It's going up significantly slower, I guess, than the previous example, but it is going up. Therefore, the limit as x approaches infinity of g of x is infinity. Okay? And then the last one, the limit of h of x as x approaches infinity, we're told h of x is 3 to the power of x. Okay, h of x is equal to 3 to the power of x. If we think about what that looks like on a graph, this is an exponential growth function, and so it looks something like this, right? So as x is approaching infinity, right, our y is obviously shooting up again, similar to the x squared, right, 4x squared. So in this case, as x is approaching infinity, as x is getting bigger, our y value is also getting bigger, and it's never going to stop doing that. So as x approaches infinity, h of x, the value of that function, is approaching infinity. Okay, so what I want you to realize here is I just did 3 limits, and they're all exactly the same thing. Right? All of the limits as x approaches infinity for these 3 functions, they're all infinity. The question for us today is, are all infinities created equal? The answer to that is no, and that's what we're going to talk about using problems 3, 4, 5, and 6. 3, 4, 5, and 6 in chapter 8. Okay, so if you look at number 3, which for you guys is on page 372, maybe 372, 371, 372. Somewhere in there, you'll notice that the problem is entitled The Race to Infinity. We are given 8 different functions, a, b, c, d, e, f, g, and h, all different functions. And what we're going to be asked to do is essentially create a table that looks something like this. Okay, so we're going to make a table where we list our functions. We find all of their values when x is 1, when x is 10, when x is 100, when x is 5,000. Okay. And this is part A of number 3. This is part B of number 3. This is part C of number 3. This is part D of number 3, okay? So if I write out the functions, the first one is 50 times the square root of x. And then the second one is x to the 10th. The next one is 100 times x squared. The next one is 800 times the log of x. And then we have 2 to the power of x minus 1,000. Then we have x, just regular x. Then we have 1.1 to the x. Then we have 20x to the third, okay? So we're going to go through these functions. We're going to find all these values, and we're going to talk about what that means in terms of the race to infinity. Who's going to win the race? Who's going to lose the race? Who's fast? Who's slow? And so on. Now, all of these functions are approaching infinity. Okay, so let me say that at the beginning. The limit as x approaches infinity for all of these functions is infinity. The limit as x approaches infinity is infinity. They're all going up. The question is, are they all going up at equal speeds, right? Or does their difference in speed affect anything? Okay, and the answer is very much a yes. So if we start, let's just say with 50 times the square root of x. If I were to put 1 in for x, the square root of 1 is 1, so this becomes 50, right? If I go to x equals 10, if I do the square root of 10, multiply that by 50, I get 158.11. Okay, 158.11. Okay, when x is 100, the square root of 100 is 10, so I actually know this one. This one's 500. And then when x is 5,000, if I do the square root of 5,000 multiplied by 50, I get 3,535.53. A lot of 3's and 5's there. Okay, so those are the values that this function a of x takes when x is 1, 10, 100, and 5,000. All right. If I go to x to the 10th power, 1 to the 10th power is 1. 10 to the 10th power is, my calculator gives it to me in scientific notation, says 1 times 10 to the 10th. So, you know, that's basically like, it's like a 1 with 10 zeros after it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is that? Thousands, millions, 10 billion? 10 billion? Okay, and then this one, I'm just going to put 10 to the 100th power. Okay, 10 to the 100th power. My calculator actually gives me overflow error, so I might write that here as well, overflow. Okay, overflow error. And then, of course, at x to the 10th, I did that backwards, didn't I, guys? Yeah, it's not 10 to the 100th power. It's 100 to the 10th power. There we go. How about 100 to the 10th power? Whoopsies. Okay, so that's 10 to the 20th. All right, that's a little better. 10 to the power of 20. So that's a 1 with 20 zeros after it. Okay, 1 with 20 zeros. And then if I do 5,000 to the 10th power, now I get 9.7656 times 10 to the 36th. So this is 9.77 times 10 to the 36th power. Okay, so that's scientific notation. Basically 977 and then 33 zeros after that, right? So obviously things are getting very big. Okay, now I'm gonna go through the next one relatively quickly. For the function c of x, 100 times x squared, this is 100. This is 10,000. And then this is 100 squared times 100. That would be 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. And then 100 times 5,000 squared, that I get 25, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay, so just through these first three functions, you guys, we are all getting bigger, right? All these functions are getting bigger, growing, getting larger, but it's pretty clear that x to the 10th is definitely in the lead right now, right? 9.77 times 10 to the 36th power is bigger than, 2.5 million or whatever, 2.5 billion, whatever this is. And then obviously that's a lot bigger than 3,535. So already we can see that we have some winners and we have some losers, some fast and some slow, right? All right, if I go to 800 times the log of x, if I do the log of 1 on my calculator, I actually get 0, right? The log of 1 is 0 because 10 to the 0 power is 1. So 800 times 0, this one's actually 0, so it starts out at 0. Then I go to log of 10, this one's going to get to 800. And then log of 100, this is going to get to 1,600. And then log of 5,000 multiplied by 800 gets me to 2,959.176. Okay, so as we can see, this one, even though it was way ahead of this guy, it was way ahead of A, right, at when x was 10, and it was still way ahead when x was 100. Now at 5,000, it's behind, right? It's losing. So that's not ideal. Okay, the next function is 2 to the x minus 1,000. So when x is 1, this is actually going to be 2 minus 1,000, right? Because 2 to the first is 2. 2 minus 1,000 is negative 998. Negative 998. Okay, so when x is 10, 2 to the power of 10 minus 1,000 gets me to, minus 1,000. 2 to the power of 10 minus 1,000 gets me to 24. So I'm up to positive already, but still way behind, right? Way behind. Now 2 to the 100th power minus 1,000, I'm at, something in scientific notation. 1.27 times 10 to the 30th. 1.27 times 10 to the 30th power. So, I went from being in dead last to suddenly I'm ahead, right? I'm winning the whole thing because 10 to the 20th and this is 10 to the 30th, so I'm winning. Now, when I go to the 5,000th, 2 to the 5,000th power, this is where I get overflow error. So this I'm just gonna put overflow, meaning this number is so gigantic your calculator cannot even represent it in scientific notation. Okay, so it's huge. It's unfathomably large. The nice thing about x, this next function, is this one's pretty easy because x is 1, x is 10, x is 100, x is 5,000. Okay, 1.1 to the x, 1.1 to the first power. This is 1.1. So again, not starting out very high. And then 1.1 to the 10th power is 2.59. Yikes, right? So this one's currently losing. Yeah, it's a loser. 1.1 to the 100th power. Okay, suddenly we're at 13,780.6. And then if I do 1.1 to the 5,000th power, oh my goodness, another overflow error. Interesting. Okay, so that's an overflow. Overflow. Okay, that's an overflow. And then my last function is 20 times x to the third power. So 20 times x to the third. If x is 1, then this is just going to be 20. When x is 10, if I do 10 to the third power and then times that by 20, I get 20,000. So this is 20,000. And then this function, this is when it's 100. So if I do 100 to the third power, and then I multiply it by 20, I get a 2 with 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. And then if I do 5,000 to the third power, and I multiply that by 20, I get 2.5 times 10 to the 12th power. 2.5 times 10 to the 12th power. Okay, so there I've just done pretty much, well, I have done all of number 3 in chapter 8, section 1.1, okay? So I have each of my functions, and I have their values when x is 1, 10, 100, and 5,000. Now, I want you to take note, okay, of mainly this column over here, okay? Letter D, x equals 5,000, because this tells us the final finishing order of the race to infinity. What I mean by that is which of these functions gets to infinity the fastest, which of these functions gets to infinity the slowest. Okay, and we know that because of where they're at when x is 5,000. Okay, if it's behind now, it's going to keep creeping up slowly. If it's way ahead now, it's going to just shoot up like crazy. All right. So regardless of what was happening back here, right? So notice that obviously our dead last and when x was 1 was here, negative 998. Dead last. Almost dead last here, right? It was only ahead of 2 of them. And then in the end, it's an overflow error. So it's just gigantic, okay? So we're going to list out now the final finishing order of the race to infinity, okay? And the final finishing order, which is sort of what they want in letter D, is, let's see. So this function here, wherever my thing is, this function here is the winner. So this comes in first place. First place is 2 to the x minus 1,000. Second place is the other overflow error. Okay, and that's 1.1 to the x. Third place is, I think the next biggest I see is 10 to the 36th power. Right, so that's third place. So far, we have gone A, B, C, D. E is the winner. E, F, G is in second place. B is in third place. Anything else with scientific notation over here? Anything else? Scientific notation. Yeah, right here. H. H comes in fourth place. Okay, and then nothing else with scientific notation. So I think next would be C, comes in fifth place. And then the next biggest, let's see, what do I have left? 3,000, 2,000, 5,000. So F would come in sixth place. Then the square root guy A is in seventh place, and the log is in eighth place. Okay, so there's our final finishing order. All right. So which one gets to infinity the fastest? That is 2 to the x minus 1,000. 2 to the x minus 1,000 gets there the fastest, even though it started out the furthest behind, right? Which one gets to infinity the slowest? That's 800 times the log of x. That's 800 times the log of x. 800 times the log of x. Okay, now, these functions, you guys, are not just arbitrary, okay? Now, they have pieces added to them that we'll talk about in a second, but we have different types of functions here that we have seen before, right? We have a square root function. We have x to some power functions, right? We have x to a power of 2 or x to the power of 10. We have log functions. We have exponential functions, 1.1 with the x exponent, 2 to the x, and so on, okay? So we're going to write down a general rule for the winner of the race to infinity, okay? And then we will talk about applying this, okay? We're gonna do that, and then we're gonna talk about applying this, okay? So the finishing order in the race to infinity generally, okay, outside of number 3, but just in general, write this down in your notes, please. Okay, the winners of the race to infinity, the ones that get there the fastest, are the exponential growth functions, okay? For example, 2 to the x, or 4 to the x, etc. Okay, or obviously we had 1.1 to the x. One thing to note here, the bigger base wins among the exponential growth functions. okay? So 4 to the x is going to beat out 2 to the x. 4 is bigger than 2, so 4 to the x wins over 2 to the x. 50 to the x would win over anything lower than 50 to the x, okay? So a bigger base wins there. Second place after the exponential growth functions is x with an exponent, okay? X with an exponent, called a power function. So for example, these are like x squared or x to the 12th or x to the 400th, okay, or whatever. And in this case, a bigger power is going to win. Bigger power is going to win. So x to the 400th is going to beat out x to the 50th power. X to the third is going to beat out x squared. X squared is going to beat out x to the first power, okay, and so on. Now, it's important to note that every exponential growth function beats out every power function, okay? So 1.1 to the x is going to beat out x to the 400th. Even though x to the 400th for the first long time is going to be higher, as we get to infinity, the exponential growths eventually are going to take over, all right? Now, behind the power functions come the radical functions, and that would be like the square root of x, or possibly like the third root of x, or the fifth root of x, or something like that. These functions come in behind the power functions. They're sort of like power functions if you remember from algebra class how the square root of x is really x to the 1/2 power. So we can sort of see those together if we want. But otherwise, radical functions come in next. And interestingly, the lower index is going to win. Okay, so the square root of x with 2 as its index is going to beat out the fourth root of x with 4 as its index. Okay, a lower index is going to win. So like the 10th root of x is going to lose to the 8th root of x. Okay, and the 8th root is going to lose to the 5th root. Okay, as we make the index lower, we actually win the race to infinity. Okay, and then the last thing is log or natural log functions. Okay, log functions come in last. So, you know, we can just see log of x like from our calculator. That would have a base of 10, right? We could also see like, you know, log base 2 of x, etc. And in this case, the lower base wins. Okay, the lower base wins. So the log base 2 of x is going to beat out the log base 3 of x. Okay, so this is our finishing order in the race to infinity. The reason that this is important for us will become more clear in the next video, but we're going to spend a little bit more time just sort of going through 4, 5, and 6, problems 4, 5, and 6 here relatively quickly, where we begin to learn how these terms can dominate each other when they are in the same function, okay, when they're in the same function. And we're going to start just with these two terms here, okay, these two terms. We have x to the 4th power here, and that's going against negative 1 million x to the 3rd. Negative 1 million times x to the 3rd. So these two different functions, one is positive, one is negative, okay? They're both power functions, right? X to some exponent, but the x to the 3rd has a negative 1 million multiplied onto it, okay? So think about what that means when x is 1. This one's negative 1 million, and this is 1, right? And even when x is 2, this is negative 8 million, and this is positive 16. So obviously, the negative 1 million x to the 3rd is pulling very much negative to begin with, okay? But because the race to infinity has the higher exponent win all the time, x to the 4th is actually eventually going to beat out negative 1 million x to the 3rd, okay? And that brings up an important point. When x approaches infinity, nothing added or multiplied or subtracted or anything else, right? Added or multiplied or subtracted matters. Okay? Nothing matters besides the actual function itself, okay? Because I want you to think about if I made my x value be 400 trillion, if I do 400 trillion to the fourth power, right? 400 trillion to the fourth power, that's going to be a lot bigger than a million, right? And so this 1 million, even though it's a big number, in light of infinity and in light of 400 trillion or 700 quintillion to the fourth power, it's meaningless, okay? So just like if I were to do, if I scroll back up to my race to infinity, remember that 2 to the x started out in last place because there was a minus 1,000, right? Because there was a minus 1,000, it started out way behind everything else. But as we get to infinity, as we start doing 2 to the 100th power or 2 to the 300th power, right? When we get to these numbers that are in the millions, billions, trillions, quadrillions, does minusing 1,000 really actually matter? Right? Like think about if you have $1 million and somebody asks you for $1,000, I mean, it seems like a lot of money, but it's like less than 1% of what you actually have, right? It's like 1/10 of 1% of what you have. So in light of these gigantic numbers, anything added, subtracted, or multiplied, right? Like this 800 times log of x, in the end, that didn't matter either, and it still lost, okay? So nothing added, subtracted, or multiplied matters at all when we get to infinity. So x to the fourth is going to be the winner of this race to infinity between these two, okay? So what that means is if we have a function that says this, d of x is equal to x to the fourth minus 1 million times x to the third, okay? So think about what's happening here. Minusing 1 million times x to the third. This term, 1 million x to the third, is pulling us down, right? This term is pulling us into the negative because it is being minus. It's a negative. So it's pulling us down. This term, x to the fourth, is positive, right? So what we have to decide here, if we're thinking about, the limit, whoops, that's not very good. If we're thinking about the limit as x approaches infinity of this function, which, by the way, is number 5, limit as x approaches infinity of d of x, which one's going to win, right? That's the question we're asking. Which one's going to win? The one that's pulling us to the positive or the one that's pulling us to the negative? And that's a question of who wins the race to infinity. Which of these terms is more dominant? Okay, that's what we call the winner of the race to infinity. We call it the dominant term. Okay, so in this case, x to the fourth is my dominant term. So the dominant term is the one that wins the race to infinity, and that can inform us of what the limit as x approaches infinity of this is going to be. It's going to be positive infinity because the positive wins out against the negative. Okay, positive wins out against the negative. Now, number 6 in section 811 asks us to look at a bunch of polynomial functions and determine what is the dominant term. Okay, and not only that, but we're also going to talk about the limits as x approach infinity, and we're going to use letter A as our example. Okay, I'm going to do letter A, and then you guys are going to do B, C, and D. So for letter A, it says negative 2y to the fifth plus 10y to the third plus 400y. And they're asking us which of these is the dominant term. Okay, which of these is the winner to the race to infinity? Now, even though the last term has a 400 multiplied on, that doesn't matter, right? All I'm looking at is the actual function. And so because I see a variable, right, my variable here with a 5 power, this term is going to be my winner. This term is the dominant term. It's the winner of the race to infinity, okay? So when I'm then asked, or if I were asked, what is the limit as x approaches infinity of this function, the limit as x approaches infinity of this function, I don't care about anything besides the dominant term, okay? Besides the dominant term, I care about nothing, which means I don't care about 10y to the third, and I don't care about 400y. So if I want the limit as x approaches infinity of negative 2 times y to the fifth, well, I just think of, okay, I should actually have this be the limit as y approaches infinity, not x. My fault there. Limit as y approaches infinity. Put a big number in for y in this case, say 200, and do 200 to the 5th power, 200 to the 5th, because that's what y to the 5th would be, times a negative 2. I get negative 6.4 times 10 to the 11th. So notice this is negative. Why is it negative? Because it's being multiplied by a negative 2. Okay, so once I've identified the dominant term, I can simply X off everything that's not the dominant term. I don't care about anything else. Because as y approaches infinity, these two pieces are not going to matter at all in the end, okay, because they're going to be small potatoes compared to negative 2 times y to the 5th. So in this case, because my number is negative and it's very, very large, my limit here is negative infinity, okay? My limit is negative infinity. Now, a similar question or a related question that I want to address, because it does come up in your homework, is what if I had y approaching negative infinity? Well, exactly the same thing is true here, okay? So the limit as x approaches negative infinity, I'm still going to try to identify the dominant term, okay? But then I'm just going to imagine myself putting a hugely negative number into the function, okay? Now, for some of them, it's not going to make any sense, okay? It's not going to make any sense at all. For example, when we go to negative infinity, so I'm going to put over here, when x approaches negative infinity, exponential growth functions, right? So like 2 to the x, 3 to the x, they disappear. Because if I were to raise 2 to the negative 10th power, right, that would be 1 over 2 to the 10th, they become really, really small fractions. So exponential growth actually disappear, okay? Exponential decay functions, so when we're going towards negative infinity, we're looking more for things like 0.2 to the x, where it's smaller than 1, okay? A base smaller than 1 is going to win the race to negative infinity. And then obviously log functions don't even exist in the negative, so they are out. Square roots don't exist in the negative, except for odd indexes. So things get a little bit more complicated for negative infinity in general. So in your homework, we're just focused on negative infinity for polynomials, okay? So for x or some variable 2 powers of this number, that number, whatever. So again, we're going to try to identify the dominant term. I've already done it here. So now I just imagine putting a hugely negative number in. So let's even put, like, not even a huge one, let's put in negative 10. If I do negative 10 to the 5th power, I get negative 100,000. Okay, so my y to the 5th, when y is going in the negative, is negative, right? Because a negative number to an odd exponent is a negative. Now I'm going to multiply it by a negative 2, and look at that, it flips to positive 200,000. Okay, so when y is going to negative infinity, this function is actually going to positive infinity because y to the 5th is now negative, and when I multiply a negative by that negative 2, flips to positive. Okay, so when we go to negative infinity, we have to think. We have to think more about what is my function doing, what happens when I put a giant negative number into that function, and what happens when I then multiply that by a negative or a positive or whatever it is. Okay, so do some thinking on those things. I'm going to have you continue with number 6, just identifying the dominant terms. You don't have to do the limits because then you have to do that in number 7, okay, number 7, and then you have to do it in number 8, going to negative infinity, right? If you have any questions about the race to infinity or how it affects limits of polynomials where multiple terms are added together, please let me know. Reach out to me. I know this was a lot, and I know it was sort of a long process, but I promise as we get better at the race to infinity, you'll see the application tomorrow makes our lives quite a bit easier, okay? So if you need something, if you need help, reach out to me, let me know. Otherwise, that's all I have for you right now, and we'll talk to you soon.